actually may already revise them from our previous lectures. Please find that every lecture, some of the lecture now have written that you have to revise the tasks and the task number, and you actually have to be ready to make the calculation. So I would like to ask you to review the way how these tasks are solved, and then you may try to perform the task what is actually will be on you. I still have not yet put the calculation of the filter. It's I have no, it's actually my own problem that I have no time to do this, but nevertheless I still have not put on the Ortus now. But now you have another type of the tasks, and you may review them. You have to review them too. So I'm just looking at Ortus. Did I find it? Should be this one. So looking at Ortus. So here you could see this is of problems for the course part 1, and you may already already actually review the problems from 1 to 3 from this course, and you may review, I guess, the problems number 4 and 5. So up to this, so up to from 1 to 5, you actually I probably put it in Ortus too, so you could freely review these problems and try to find whether you could solve those problems. And up to the next class, I probably will put some homework assignment for this simple calculation of some parameter of measurement, analog measurement devices. Well, so let's go back. So we actually stopped here with this some special types of the amplifiers, and let's discuss a little bit very important device. What actually probably already you have some experience working with this. I hope you may work with such a device on your physics classes and your electrotechnic classes. So it's an oscilloscope, actually the core, the main device of any electronic engineer. So actually I could imagine how could we check the design or the operation of any electronic circuit without the oscilloscope. Actually, what oscilloscope do? So it allows us to measure. Usually oscilloscopes are the devices as a let's say tabletop devices. They actually use designed to measure voltage. So it's actually a voltage meter. So they measure voltage that change in time. The measured voltage usually is depicted on the screen in the shape of a waveform, and from this depiction, so we understand that we have to that this oscilloscope actually have two indications. It indicates time in somehow, yes. So it's the indication is related to in time. So the special part of the oscilloscope, what is called sweep, yeah, provides this sweep module, sweep block, provide the movement of the okay. So the signal is actually depicted on the screen as a spot, as a bright spot, and the sweep provides the movement of the spot in horizontal direction that is related to the change in time, and the amplifier, embedded amplifier, provides the movement of the spot in a vertical direction, and the vertical deflection of the spot is proportional to the amplitude of the measure, to the value of the measured voltage. So, and combining these two movements, horizontal movement because of sweep and vertical movement because of change of input voltage, we got the shape of the signal. So we may observe the shape of the signal. And the corresponding, the modern oscilloscopes, which are actually digital devices, do the same. So they move some bright point on the screen in the horizontal direction because of sweep, and the vertical direction because of the amplitude of the input signal. The control of the oscilloscope, whatever it, actually all the controls that oscilloscopes have, even now it's a digital one, they are actually originated from the analog one. So we have a possibility to change the rate of sweep. By this we change the time scale. So the faster the point moves, the smaller is the scale, or smaller is the range of the time scale. So if we move very slowly, so the time when the point travels from one end to another, it will be quite high. So we have a big range in time, but it's not good for depicting of fast processes, because all these processes will just glues together and we just see only a white bright band. For the very fast sweep, we have a very small time, but from this all very small time correspond to this movement from right to left, from left to right. So we may use it for the depiction of the fast processes. So the one control what usually oscilloscope has is this time range. With changing the time range, we actually change the speed of the sweep. Second is the voltage range, which actually related to the internal amplifier. By changing the gain of the amplifier, we change the scale of the vertical direction, and this allows us to depict a different. So actually, by changing the voltage range, we change the amplitudes that we are able to depict on the screen. By increasing the gain, we actually decrease the range, and we may depict smaller voltages. By decreasing the range, we may depict a higher voltages. Very important thing in oscilloscope is so-called synchronization. So if we imagine that we try to draw graphs, so we draw some graph on the oscilloscope, draw the graph on the screen, and then it starts to draw it from the beginning, one more. So it's usually we got the situation when the next drawing is actually overlapped with the first drawing, and they are not when they are not synchronized, the new drawing, the waveform of this signal will be drawn from the other starting point. That's why all these separate drawing overlaps and make such kind of wide and bright ribbon on the screen, and we couldn't distinguish a separate waveform on the screen. To prevent this from happening, we have a special model in the oscilloscope, which name is synchronization model. And what the synchronization do? It's actually follow the level of the signal. We call it sync level, and we may adjust it, take it higher or lower. So the electronic of the scope follows the sync level and wait when the signal amplitude reach particular voltage level, and start to draw the waveform of the screen. To actually start the sweep only at this moment when the voltage reached this synchronization level. There is another additional condition. So we have to got here the rising signal or falling signal. So there is besides the synchronization level, another control what usually oscilloscope have to which a change of the signal level to react. Either we could react to the increase of the increasing edge of the signal, or we could react to the falling edge of the signal. But the point from of the particular event which starts the sweep is when the signal amplitude or signal level reached this preset synchronization level, and the signal is either growing or falling. It depends on the setup of the scope. So usually we set some level and growing signal. Sometimes the falling edge may be of interest, so and then it's draw from the falling edge. Why do we actually need the edge here? Because when we look of the shape of the signal, for instance, sinusoidal signal, there is two over the period. We have 2 points, 2 time instants when the signal is equal to the certain level. So one it's on the rising edge, and second on the falling edge. We actually have to select one of them. And that's why we set the synchronization by choosing the level and choosing the edge, rising or falling. Another control what usually we have here is the channel selectors, and we could change the channel we were working with. The modern oscilloscopes are usually have several channels. It's much more convenient. For instance, this is a 2-channel analog scope, and this is a 4-channel digital scope. Usually, the number of channels for some kind of average cost scopes will be 2, because it's very inconvenient to work with one. We often are interested to look at what is signal of the input of our circuit and what is the signal of the output of our circuit. And to see it immediately, see it simultaneously, we have to have 2 channels. There is quite for the digital scopes, the amount of control with digital scopes here is much more higher than for analog. But the minimal thing, and what certainly any scope could have, it's a time range selection, it's a voltage range selection, it's a selection of a synchronization level, it's a selection of channels, and it's 2 additional regulation, so-called Y offset and Y offset. So we could actually move not only Y offset, it could be time offset too. We actually could move the whole picture up or down, left or right, just moving the whole picture. To make it more convenient to observe, and it's a mode selector which allows us to select how the scope works with the AC and DC signals. So we have a DC mode. For the DC mode, the signal is depicted as is, and we have an AC mode usually in a scope. For the AC mode, the constant component, the bias, the DC bias or DC component of the signal will be eliminated. So for the DC view, so if we have some, so it's actually the difference is that when we connect it to the AC mode, so the capacitor is connected in series with the signal source. So actually, if we have some DC component, so it will be eliminated. If we take a DC voltage and connect to the scope in DC mode, okay, we will see just that the line of the scope just jump up or fall or moves down, depending, we have plus or minus of the voltage, so it goes up or down. But if we connect the DC signal to the scope in the AC mode, the line which depicts the signal will not move at all. It's because the capacitor on the input just eliminate any DC component. And the third mode, usually what is actually could be used, could be attached to the, could be switched for the, could be set in the scope. It's a ground mode when we just ground the input. So it doesn't mean that we ground. It's important. Technically, this grounding happens internally. So it just means from the connector point of view that the signal connector is just disconnected from the scope, and the inputs of the amplifiers inside the scope are connected to the ground. So when we connect to the ground, we will not burn our signal source or will not shortcut the signal source. We just put the zero ground level on the input, and this is usually we use this mode just to find where the zero of the scope is, and using this Y offset to move it in a convenient position. So sometimes, for instance, if we know that all our signals will be positive, so we may move the signal, all the picture down to use all the range of the scope screen. Or if we know that they will be negative, we may move it up to take the whole range of the scope screen, and so on. So the construction of the scope, so how it's designed actually. So this is a view of the analog oscilloscope. So what we actually have here. So here, as I said, this is this. So first of all, we have the sweep generator. So the analog scope, in operation of the analog scope was based, or actually the heart of the, I would say, the most important part of the analog scope was the cathode ray tube. It's actually cathode ray tube. It's it's a rather big vacuum device, like a vacuum lamp, where we have a electron beam source. Usually, it's a hot spiral. Yeah, it's a hot spiral which, like in light bulb, when we heat it with a current, it emits electrons. So those electrons with a rather high voltage was accelerated towards the screen. So the voltage for the X-ray for such kind of cathode ray tube may range from 300 up to 700 volts. It depends on design of the tube, but it's quite high because we have to get a very narrow, very well focused electron beam. To get this beam, the series of anodes which actually provide this difference in voltage between cathode and anodes. So we have here high voltage. These anodes have a particular shape and operates, so this looks like a concentric rings placed on the way of the beam, and they works actually as a so-called electron lens. So it's focused together all the electrons and shape a narrow beam projected to the end to the screen in the relatively small spot. There is some details of how to feed or how to connect this cathode tube to the electricity, but generally what we have to get the anode and the screen, it's at the same potential. That's why very often the screen and anodes are grounded, and the cathode is under the high negative potential, so it actually repulses the electrons that are produced on the cathode towards the anodes, and anodes work. So it's, from electricity point of view, it's not it's absolutely the same situation whether we put 0 voltage to the cathode and plus to anode, or we put 0 to anode and minus to cathode. So the potential difference will be the same. So this beam, this narrow beam, goes through 2 pair of plates, just metallic plates. It's nothing else. It's really made from metal. 2 plates, and these plates provide deflection of the beam, either in horizontal direction, so call it X plates, or in a vertical direction, it's a Y plate. The deflection of the beam happens when we apply some voltage to the plates, just plus and minus. So this voltage should be quite high too, to have to provide enough force to deflect the electrons, which are actually moving quite fast because of the relatively high voltage. So this voltage should be quite high too. So they actually somewhere in the range about 50 volts for the analog devices, analog scopes. And this voltage in turn are controlled by the 2 modules inside the scope. So this, as I mentioned, sweep generator, which actually provides some kind of saw-type waveform. So the voltage grows slowly, providing, so it's actually jumps to some negative value, let's say, relative negative value, some negative values, and we understand the negative direction in the. Yep, some question, please. You may ask immediately. Yep. So it's we got some negative. I understand the negative. It's this direction of the voltage which deflects the beam towards the left side of the screen, and then it grows. It grows actually relatively slowly, providing that the beam deflects less. Finally, when the voltage is 0, the beam have to be directed into the center of the screen, and then the voltage continue to grow, and beam is deflected in the another direction, in a positive direction. So this kind of sweep provides a movement. In fact, what happens as a result, this point where the beam touch screen, or the beam fall on the screen, will just move in horizontal direction. Then very fast the voltage drops back to negative, and very fast the beam jumps back to the beginning of the screen. Sometimes, not sometimes, but in more or less qualitative scopes, this at that moment when the sweep voltage reach its maximum, the cathode, actually the voltage which is applied to the between cathode and anode is switched off. By this we just block the beam, stops the beam, and when the voltage falls down from the maximal to minimal, we have no beam, so that's why we don't see how the beam goes back. But it's actually sometimes this movement is so fast that we even couldn't notice it. So it's maybe sometimes for the very first simple oscilloscopes that no one actually care about the switching the beam off. But in the modern scopes, it may be switched off at the period when the beam come back, when the voltage come back. So this is a sweep generator. It controls the horizontal movement of the beam. The vertical movement of the beam is controlled by the Y amplifier, which is just accept input signal, amplify it up to the voltages that cause a noticeable shift or noticeable deflection of the beam. And if the voltage is changing, so this voltage, or if the input voltage is changing, so the voltage on the plate is changing too, and the point where the beam touches the screen is moving. It moves up and down. So by combining these two movements, the horizontal movement because of sweep and the vertical movement because of the change in the input voltage, we actually, the beam actually draw a line on the screen. To visualize this line, the screen is made out of luminophore, the material which actually which emit light when the electron beam strike it. So, and we see the bright line on the screen. The regulation what we had, so the time scale, if we need it. So what does the time scale do? The time scale actually change the slope of this sweep voltage. So the higher is the slope, the faster the beam moves from one side to another of the screen. So we just change on the slope of this line, so with the time scale. Taking a bigger scale, the slope is slower, so the movement is slower. For the narrow scales, in the very small times, for the small times instance, for the fast processes, so the slope of the beam is higher. The horizontal position just moves this waveform up and down as a whole. So we just add some DC component to this sweep voltage, and then we get the let's say the initial position of the beam is moving right and left, moving just right and left by adding here either positive or negative or positive DC component. For the with Y amplifier, the same. The voltage scale change the gain of the amplifier. Hereby, it's actually changed how far the beam deflects with a given input voltage. And vertical position the same. It's add a DC component to the resulting voltage that is applied to the Y plate, and the DC adding of the DC component just moves this starting point of the beam up or down. So all the process will happens in respect to the starting point. This switch, AC-DC mode switch, as I said, is just connect or shortcut, is a connect or shortcut and a capacitor on the input. So for the DC, the switch should be switched on, and the signal goes bypassing the capacitor. For the AC mode, the switch is disconnected, and the signal goes through the capacitor. Thus, the DC component is cut. The triggering process, so the triggering of the sweep generator. So we have this trigger model, which actually is related to the amplifier. So it's actually follow the voltage what amplifier transform. So here is the voltage which is proportional to the input voltage, and the level of the synchronization is set here in the trigger model. So like a comparison level at which the trigger model have to provide a pulse to initiate this sweep generator. So this is a design of the analog oscilloscope. Actually, it could be indeed made entirely analog because all the sweep generator and the trigger models and all they are actually analog circuitry, except probably of trigger mode when we have to use some comparator. But anyway, some simple logic on the level of AND or NOR gates, it's enough to build an analog scope. So we still need some logic here and comparators. What is the difference between actually between the digital scope? So the digital scope it's a microcontroller which has some memory. Usually we have some memory, and that provides a clocking by itself. And by changing actually the time scale control or triggering control, we actually change the program of this microcontroller, which what are actually doing is measure the voltage in a certain separate amount of time. These measurements are controlled by the internal clock of the microcontroller, So by changing the let's say the time instant between the time between those instances when the measurement is taken, we change the time scale, so we may record the data more often or not so often, and the measured voltage actually is converted with the analog digital converter, transferred in a digital form, and the scope actually depict it on a screen, on some kind of screen, as a computer do. What actually still have not related to the microcontroller, may not be to related directly to the microcontroller, we still need an analog amplifier here. We still need an analog amplifier because we need to adjust the output voltage of the amplifier to the ADC input voltage. So we could adjust the signal to the analog to digital converter input voltage. So we need this analog amplifier. So we couldn't get this output. So we have this amplifier, and the regulation of the voltage scale and vertical position is actually the question of how this analog amplifier works. So with the vertical position, so there may be some different solution, different way how to design, how to provide this vertical position. We may add it actually with a already converted the analog to digital signal. But sometimes, but generally, it's better to have this vertical position. In fact, adding to the input voltage, because we may correct a little bit the input voltage without losing of data or after during the digitization of the signals that occupy a wrong range. So we could use this vertical position change in analog form and add it to the output of the amplifier. So the difference between actually digital scope, so between analog scope and a digital scope is that we actually transform the measured voltages in a particular amount of time in a digital form. I actually, to my mind, even independently, whether the analog scope is, when the oscilloscope is analog or digital, is the signal that is sought for the measurement, sought to be used to measure analog signal. And up to if the operation mode is selected correctly and the scope parameter it's satisfactory to measure particular signal, we actually have no any difference whether we have analog scope or a digital scope. The digital scope, of course, it's more functional in this way that we can store data. In analog era, before the digital scopes appeared, so the problem of storage of the pulse, for instance, you observe some short pulses and you wish to see how this pulse looks like. With analog scope, it was a very hard task because if these pulses are very short and come very, very rarely, so you may actually have no time to see this pulse because it's appear and disappear immediately. So there was some special so-called memory luminophores, which actually accumulate data and have a very long afterglowing period after the excitation. But this was really headache to get to remember to fix somehow to record somehow the short pulses. With the digital scope, it's not a problem at all because all the data are actually written down. And in memory, we may stop the measurement and recall the data from memory. Hereby the scope, of course, they have intrinsic memory, so we have not to care too much about the storing the short pulses, the shape of the short pulses in somehow. So they are already will be and recalling these signals. So we get we have a memory already, and we may recall the signal from memory when we wish. So it says here is just some examples of about scopes. This is a scope that we will use, I hope we will use in our laboratory classes. So this is a scope which is connected via USB to the computer, and it's a two-channel scope. So it has two channels A and B. You can observe simultaneously two signals, and this scope has a very useful feature. It has a function generator built in. So the third connector is actually an output connector for the waveform and function generator. So it could produce a sine wave, a square wave, triangle wave, and we even may provide a set of data for this generator, and this generator will generate the signal of our own shape. So we may simulate any shape for this generator. So for this, we just have to write down a long in Excel for elsewhere to get just a set of numbers or some set of numbers which describes the relative amplitude of our signal over the one period. And the generator takes this data and produces a signal of any repetition frequency what we want. So for example, we may simulate the ACG, we may simulate a blood flow waveform. So we may simulate whatever using this function generator. The generators, usually the scopes, usually use so-called B and C connectors. It's a very popular connector for the high frequency signals. And nearly any scope you will find in your life will be equipped with these B and C connectors, so please be ready to work with them. So they are quite robust, yes, and they have special lock that allow you to connect it. You just put a plug over the socket or inside the socket, turn this lock, and you get the connection that actually couldn't be so easily disconnected. So be careful when you disconnect it. Don't just pull. You have to turn lock first to open the connector and then remove the plug from the socket. So this BNC connector is one more. So one of this golden standard connector for the high frequency signals. So the probe, the scope probe itself. So it looks like this. So it's a typical scope probe with a BNC connector, with a probe tip. There is two types of the tip. One tip, just like you may put it to a certain point in your circuit, and another tip, this, how to say this, so this detail, which is actually here, it's some kind of cover which is put on the tip of the scope, but this cover usually have a hook integrated inside. So you may, when pulling this part towards this direction, you will expose the hook. So you may take this hook to connect to some wire. Use this hook to connect to some wire. So the other, so the tip, usually we name it a signal wire. So it comes to the central. It is connected to the central electrode of the BNC connector, and this is, we name it a signal wire. We needed two wires to connect to the circuit. The second wire is so-called ground wire. Is connected to all the metallic part of the connector itself, and actually usually is connected to the circuit ground. All the ground, let's say, connections, or all the grounds of the particular individual connectors which are within one scope, within the construction, within the design of one oscilloscope, they all are connected together. So the ground of this BNC is connected to ground to this BNC and to this BNC, and they all connected together with the ground of the scope and to the ground of the USB connection. So all the grounds are connected together. So please be careful when you work with a generator. Don't touch the signal. Don't touch any of the bodies of these BNC connectors or ground, because they're grounded with your generator signal pin. So you may get a generator damaged. So this scope, and that's actually this crocodile connector is for the ground. You may attach it to the ground of your circuit to get some measurements. And here says, here is the BNC connectors which are connected to the oscilloscope. The probe itself is not so simple. Yes, here we have a coaxial lead wire, coaxial cable, which provide the connection. And generally, the probe is not so primitive construction. It's not just a pin connected to the core of the cable. If you look, if you take whatever probe and you look, examine this probe, you will find somewhere some knob for the regulation. Usually it's made by the screwdriver. So often the screwdriver is here, is added to the kit of the probe. When you buy the new probe, you will get it in a bag, in a plastic bag with the probe itself, and all these components very often is detached. For instance, the crocodile wire sometimes is detached, and we have this screwdriver for the regulation, some kind of colored rings. You may actually remove the original ring and put the ring what you wish on it. It's easier to easily recognize which one, which end, or which BNC plug corresponds to which probe. If you use more than one probe in your work, it makes the recognition of the probe easily with these colored rings. The probe itself has some compensation circuits. So if we look at the probe, usually we have some. So the probe has a switch. The switch, by moving the switch, what we actually could do when we move the switch, we introduce a 9 mega ohm resistor in series with the cable. So why we actually need to do it? Because all the scopes, if it took any standard scope, whatever it is, digital one or analog one, so the input of the scope could be it's quite important now, so probably make note of this. So the input of the scope has some certain internal resistance, input resistance, and input capacitance. And all the scopes which now are on the market are designed in such a way to provide this input resistance equal to 1 mega ohm, and input capacitance is usually either 22 picofarad or 47 picofarad. So the input capacitance may be different, but it's usually it's stated in the data sheet or in the passport or in the technical details of the particular scope. So when you buy a scope, so usually you will find what is actually the input resistance and input capacitance. The most often the input resistance is 1 mega and input capacitance, if I remember correctly, 47 picofarads. Why do we need it? Why do we need to know this? Because when we are actually planning some measurement with a scope, very accurate measurement, we have to know what is actually the effective input resistance and input capacity of our measurement device. So because when we measure, very often we measure in high frequencies, and at the high frequency, the effective capacitance of the measurement device is actually very important. So we have, when we design our measurement circuit, when we're going to measure something and really be sure that we measure a real value, not some kind of shifted or incorrect value, we have to take into account the actual electrical parameter of our meter. So this actually, when we know this one, that the input capacitance is 1 mega and resistance 1 mega, input capacitance is known, we may make a correction on this capacitance and resistance and know the accurate voltage, measured voltage. Because when we measure, it's the same situation when we speak about measurement with a voltmeter. So we may measure with a voltmeter, but we have to remember that the voltmeter has its own input resistance. Yeah, and if, for instance, the resistance, for instance, we are going to measure the voltage over some certain resistance in a circuit, and if this resistance has if the resistance that which voltage we're going to measure is compatible with the voltmeter resistance, so then when we attach a voltmeter to this resistor, we actually shunt it, and part of the current will be driven through our voltmeter, and this change totally the current in a circuit and may change the voltage of this resistor. So when we are going to measure very accurately, we always have to take into account the actual internal resistance of the voltmeter. And here is the same. So when we are going to measure accurately, we have to know that we have to take into account the input voltage, input resistance and capacitance of the scope. And what we doing why we have a switch here? So what the switch do? So the switch connect, if required, connect this additional 9 mega ohm resistance in series with our measurement signal. So what we actually got? We actually got here a divider. So this internal probe resistance and scope internal resistance of 1 mega ohm form a divider 9 mega ohm, 1 mega ohm, which actually leads to the so what this divider do? It's actually put only 1/10 of the input voltage to the scope input. So by switching this, by let's say moving the switch, by connecting this 9 mega resistance, we actually uh, attenuate the input signal attached to the probe 10 times. So this actually expands the range of our scope. Generally, the input of the scope works up to, let's say, 20 volts. You know? So here we may increase it up to 200 volts and work with the 200 volts. So it's just using as attenuator. But when we attach it, then we may see that the capacity of the probe itself, of the cable of the probe, it has some parasitic capacity. The coaxial cables always have a parasitic capacity. So this parasitic capacity change a little bit, alter a little bit the frequency response of our scope and made it a little bit worse. So we actually may feel the effect of the probe, of the long probe, on the measured device. To compensate for this parasitic additional capacity of the cable, what is actually depicted here, yeah, like this one. The probe have inside the adjusted capacitor, the capacitor that could be adjusted, and we actually do this in this mode. We actually switch the probe to the this 10-time attenuation, and we put the signal, this rectangular signal of the frequency 1 kilohertz on the input of the scope via the probe. And then we regulate this, we adjust the capacitor by just turning corresponding knob with a screwdriver to until we have this 1 kilohertz signal depicted on the screen as accurate as possible. So this is a wrong situation. So we have some spikes, yeah, and it means that the probe effective capacity doesn't match well with the scope effective capacity. Here we have some, let's say, depression of the signal, so it's changed slower than we need. And this is actually the well-regulated probe when we see the rectangular signal as a rectangular signal. So this is actually the operation that usually have to be done when you connect a new probe, when you buy a new probe and connect it to your scope for the first time. So you have to compensate probe, to check whether the probe work well. To get this, nearly every scope what is manufactured now has an output of 1 kilohertz. So here you could see that this actually output very often it's not a BNC output. It's usually like a small metallic pin. So here you see the scope which is actually attached to this pin. Yeah, we have this output somewhere. I remember somewhere here too. Yeah, we have this in the analog scopes, and we even have it in this pico scope. So there is some small. From the side, it doesn't. We couldn't see it here, but from the side there is some hole when you put your probe, and it's the hole when this 1 kilohertz rectangular signal is generated, or otherwise you may just generate it from your function. No, sorry, probably yes. It's you use it here. The function generator. It has its own function generator. You just set the 1 kilohertz, 1 volt signal and see how it's depicted. So it's enough to use. Yeah, you may use here this own generator. But I guess it was some additional input to output too. Well, so it's shortly about the scopes. I just suggest some 5-minute break before we start speak how to measure phase and frequency. Mind you? Yep. Okay, let's take 5 minutes break until 13:25. Yep. Yep. Well, let's continue. Is it fine with the sound? No. So, uh, about the measurement of frequency phase. Let's remember just what we understand as a frequency. Uh, so for the frequency, when we have some periodic signal, so we understand that the frequency is a reciprocal to the period. Yeah, where the period is a time between the two similar signal, let's say, points. Yeah, so when we have is the time between maxima or the time between zero crossing and so on. So as a phase shift, we understand when we have two waveforms. So these waveforms are similar by their shape, but they just shifted. So the one waveform comes to the same state as a second another waveform just in another time. So here we have two sinusoidal waveforms that are shifted by the time delta t. So this is a difference. So, and from this we actually clearly understand how we measure the phase shift for the periodic signal, especially for the harmonic signal. When we speak about phase shift between two harmonic signals, so we describe them as the sine of the omega t. The omega is a circular frequency, and the shifted signal actually has an additional phi, which is added here, which we name it phase shift, or phase difference, phase shift. And this actually means that if we compare the U1 and U2, if the phi is a positive, does it mean that when the time is 0 here, and the value of the sine argument is actually omega times 0, is actually 0. So for the second signal, the value of the argument is already will be phi. It means that sine already have a time a little bit to progress. So for my picture, if we interpret the A and as the blue signal as the first one and the violet as the second one, so for this equation for this equation to be correct, we have to admit that phi is just negative. So the A already is moving, so the time already progressed. The first sign is already moved, but the second one, because of negative phi, negative phase shift, still has sinus equal to 0 here. Yeah, so if the phi is a positive, so we say that the signal is actually earlier, so it starts earlier. So we have when the positive shift, the positively shifted signal will start or will already proceed earlier than the referent one, and with a negative shift, this actually is delayed a little bit. So the phase delay corresponds to the negative phase shift. Well, we express it very often. We could express. We usually express the phase shift not in an item of time, in the units of time, but we express it as a part proportion of the period. We may express it as a proportion of the period and speak about the phase shift, which is equal to the half of the period or the quarter of the period. Here, the shift is exactly the quarter of the period. So if the total period is here, and the phase shift by time shift is this one. So this corresponds to the 1/4 of the period. But either we express this in a unit in a unit of radians or degrees, and if we're going to express it in a unit of radians, so we just have to take this shift, express it in a part of the period, multiply by 2 pi. So we got it in radians. If we multiply it by 360, we got it in a grades. And one of the simplest ways to estimate a phase shift between the two signals is to use this oscilloscope and just look at the one waveform and another waveform, depict them simultaneously on the scope screen, the two-channel scope screen, and just to measure the time between the points with the same phase. This one we have to remember one important aspect, which points to select. And there is two approaches. One approach is maybe it's a little bit more simple. We just may take a maximal point or minimal point. This approach has an advantage that it doesn't depend on whether our signals are shifted, has some DC bias or not. So the maximal point is unique for the whole period, and the minimal point is unique for the whole period. So the advantage of this method when we take the maximas is that we actually, it's no matter whether our waveform are shifted as a wall up or are shifted as a wall down. So we always define the maximum more or less straightforward and without any doubt. We know, okay, this is the maximum. The drawback of this approach that we actually sometimes it's difficult to find exact point of the maximum. So we have it's actually our you understand it is if you imagine what happens if we have a very long period. So this waveform is not so sharp. It's very how to say it's stretched, yeah, and it's has a very small slew rate. So it's very how to say it's stretched, and the peak, this maximal peak is not so sharp. It's very difficult to us visually to say where the actual maximum is, here or maybe here or maybe here. For the very so even if we stretch our t-scale, trying to find to get a higher resolution of these points, yeah, we will even with this, especially with this stretched t-scale, we couldn't be able to define this maximum very accurately. So this is a drawback. So it provides a lower accuracy. Alternative way to take the 0 point of the signal. So we take the 0 line and look where our signal cross the 0 point, and then we look at the 1 point where the look where the cross 0 point and select one of the instances, either with a growing signal or with a falling signal. So here in my illustration, I took the points where the signal is growing and cross the 0. Here it's much more easily to find the accurate time position, because we have a line that is crossing another line. So the cross point is the crossing point is defined absolutely clearly, so without any doubts, yeah. And but here we should be how to say, we should be confident that that our signals are not shifted, that the zeros of the signals are not shifted, because if it's shifted, so you could understand easily, imagine that if the violet line will be shifted up a little bit, so it means that this point will be moved left a little bit. So if we shift all the violet line up, so this point moves left, and we measure wrong time dt, delta t. So, and that's why we have to be sure that our zeros are not shifted, and then we may use this method for the measurement of the phase shift, for the non-shifted signal. The drawback of the method is obvious. We need an oscilloscope for this. The oscilloscope is quite bulky device. We may use another method to measure a phase shift between two sinusoidal signals. This is important. So for here we may look at the phase shift between any type of signals. They may be triangle signals, they may be rectangular, they even may be an absolute arbitrary shape like ACG or some kind of special pulse signal. For the pulse signal, probably the best way will be oriented to taken as the time marks, or these marker points, these maxima or peaks of some kind of arbitrary signal. For instance, ACG, we may compare the ACG signal with some by comparing when the R wave is going, yeah, so the most sharp wave. So this method is all proposed. For the harmonic signal, we may use an ellipse method. So if our signals are indeed only sinusoidal or cosinusoidal, so harmonic, for the harmonic signal, we may use an ellipse method, which actually we even have not to think about these shifts. We just depict such kind of ellipse. For the ellipse method, we use both signal, what phase shift we are going to measure, to control both channels. Most of the modern oscilloscope may be switched in a mode when the X channel or X movement is driven not by a time sweep, by the another signal. And in this way, we apply this measured both signals X, UX and UY to the X and Y channels, and actually depict one signal as a function of another. So, and then when these signals has a phase shift, we will see an ellipse on the screen. What do you think? What do you think we will see if there will be no phase shift? No. There is no phase shift. So it means that both signals reach maximum simultaneously, go through zero simultaneously, and reach minimum simultaneously. What would we see when we have no phase shift? Yes, it will be line. It will be line even more. We certainly know what type of the line it will be. It will be line that is directed from bottom left side to the upper right side. So line, let's say positive slope line. Yeah? If the phase shift is half of the period or 180 degree, so it means that the one signal reach maximum when second signal reach minimum. It will be line 2, but line which is directed in the negative slope. And what happens if we have 90 degree? It means that one of the signals reach maximum when second reach zero. It will be ellipse, but how this ellipse will be oriented? No, it will be ellipse still. It may be cycle when the amplitudes are equal. If amplitudes would be equal, we get a cycle. If the amplitudes are not equal, we get an ellipse. But the axis of this ellipse will coincide with the x and y axis. So it will be oriented either horizontal or vertical, but the long and short axis of the ellipse will coincide with the axis of x and y. But if we have a phase shift which is not exactly 90 or 180 or 0, we have the ellipse which is tilted or a little bit, not tilted or rotated, turned. Yeah, and we may find it's actually not too difficult to understand. So, for instance, when the time is 0, for taking to this example, when the t is 0, so y signal will be equal to 0, but the x signal will be equal to the amplitude y times sine phi, yeah, sine phi, and it corresponds to this point. So it's actually this point, and we may easily we understand that if it's equal to y x sine phi, it will be the signal, the value of u, yeah, at that moment will be just equal to the AB length of AB divided by 2. So it's y ux sine phi. And the maximal voltage on the x-axis, this one, could be calculated as the distance CD from the end of the ellipse divided by 2. From this, it's easily to understand that the sine of phi may be calculated as AB, this length, divided by this length. And indeed, let's imagine. So if I have such a just straight line, so CD will be maximal, but AB will be 0 because of this straight line. So A and B glues together, and I got sine phi equal to 0, as it should be. So if I have this ellipse turn it so this longer axis coincide, for instance, with this horizontal axis, my AB will be equal to CD, and I get sine phi is equal to 1, which corresponds to phi 90 degree. So, and then we get phi just an arc sine phi, just as a phase shift, just an arc sine of the length is AB divided by CD. So this is a method this method works well for the sinusoidal signals, but requires scope too. Here is an example of the design, how we could design a device which measures a phase shift without a scope and just provides some output signal that is proportional to the phase shift. The principles of the operation of this device looks like following. So we have here some amplifier which just scale our signals, and then we use the device what is named as a Schmitt trigger. Probably you remember the Schmitt triggers. So it's a comparator with a hysteresis. So actually what this does is Schmitt triggers do. It's transform our harmonic signal into such kind of meander signal of rectangular waves, or rectangular shaped waves, when the positive parts of the input wave corresponds to the positive pulses and the negative to the negative part of the wave. So, and actually it's some kind of meander or rectangular pulses. Then we send these rectangular pulses to the differentiation circuit. We use a differentiator, and what the differentiator do? It's transform these rectangular pulses into spikes, but this will be as positive spikes when this rectangular signal is growing, is switching from low level to the high level. We have a high positive peaks, and when this level switched from higher to lower, from high level to low level, we have a high negative peak. So after the differentiator, our signals for every channel will be transferred with such kind of both positive and negative peak signal. The diode just cut off the negative peak, and after the diode, we will get this signal which with our initial signal, we will transform it into the signal where we have pulses every time our waveform cross the zero and grow. Actually, this circuitry is one-to-one, is the circuitry what is used for the synchronization of the oscilloscopes. They use the same circuitry. So original signal is transformed with a comparator into rectangular signal, which actually crosses or switched from low level to high level every time the signal they overgrow the synchronization level, and switched back to the low level when our signal drops below the synchronization level. So we got this, and after the differentiation and rectification, we get a pulses. So it's depend on when we orient our or when we actually drive our scope with a positive slopes. So we actually connect this diode in a forward direction and cut out all the negative pulses. And when we going to work on the negative pulses, we actually just invert. We do the same. We just include an inverter between the differentiation circuit, inverting amplifier between the differentiation circuit and the diode, and cut all the negative, and actually cut all the positive pulses, but transform our negative into positive pulses. So this is the same circuitry what is used on the synchronization of the oscilloscope. Well, and then actually what we will get, if we have two signals which are shifted by phase, we get here after the diodes, after the rectification, we have the pulses which correspond to the particular point in the signal, particular phase of the signal. In this case, it will be zero crossing while growing point, and for this point correspond to the pulse. So we have the pulses that correspond to this zero crossing point. So if our signal has a phase shift, we understand that these pulses will be more distant from each other. If the signal has the same phase, so both these pulses appear simultaneously. And then what we actually do, then we use these pulses to drive an SR trigger. The trigger is a device which switched from 0 to 1 when the S level is switched from 0 to 1. So when we put 1 on the S input, the trigger switched to 0. When we put 1 to R input, the trigger switched to 0. Oh, sorry. When we put 1 to S input to the S input, it switched to 1. When we put 1 on R input, it switched to 0. When both inputs are at 0, the trigger will keep its last state. So if we put it into the 1 state by putting S to 1 and then drop S back to 0, the trigger continue to keep this 1 on the input. If we now move R input to 1, the trigger drops to 0. We move R back to 0, the trigger remains in the state 0. And we may several times increase R to 1 and drop it back to 0, still trigger remains in the state 0 until we will not put the until we put the 1 on S input. For such a trigger, the state when both S and R is a high level, both are at 1, it's just prohibited. We have not allowed to such a condition to occur. So we have to design our circuit in such a way that we always prevent such a situation when both S and R is at 1. Well, so here actually the first signal from first channel, so it's actually put the S to 1 and switch trigger to 1. After a while, the pulse from the second input comes and putting the R to 1 drops trigger back to 0. Actually, the output of the trigger will be 1 between these short pulses and 0 otherwise. So when the first pulse from first signal comes, it switched to 1. The second pulse from the pulse from the second channel drops it to 0. So it means that the length or duration of the pulse will be proportional to the phase shift. The bigger is phase shift between U1 and U2, between first and second channel, the longer will be this time when the output of the trigger is at 1. Then we may work in a different way. We may put this, send or read this input with some kind of digital device, for instance, with a microcontroller, which actually counts this duration while output of the trigger is at 1. But we may make an absolutely analog device if we just take this output from the trigger and put it through the mic and connect it or use it to actually to provide some currents through the microampermeter. So what happens here? So we have some pulses, and these pulses provide some alternating currents through microampermeter. The microampermeter actually accept these pulses. If the frequency of the signal is high enough, these pulses come quite frequently. The microampermeter is a mechanical device, so it's important. See, here is important to get the analog phase meter to use a mechanical device. It will not work if we have if we will have here some digital device, digital meter, because the digital meter use sample and hold approach. It's like, let's say it freeze the moment value and then transform it. So it may freeze it at the 1 level of the output and maybe freeze at the 0 level of the output. And the digital device measure here either trigger power supply voltage, and actually trigger 1 output voltage, let's say 5 volts, or 0 when the trigger shows 0 on the output. Here it's important that this is a mechanical device, because this is a mechanical device. It has an inertia, and because of inertia, when we apply such a short pulses, so the mechanical device actually make an average over these pulses. And if the pulse duration is very short, it has a very small spike, small pulses of the current, and the average current will be small. If the pulses become longer, so the microampermeter accept a longer period of current flowing, and the average of these short pulses will be higher. So actually the maximal what microamp make show here is when the phase shift reach a period actually. And when it reach a period, it means that the duration of the pulses will just equal to the period, and it means that this the trigger nearly always will be at one state, and we will get the maximal possible current. By the way, what happens if the phase continue to grow? If the phase shift continue to grow? What do you think? What happens? No, it drops back to zero. So let's imagine that this distance actually grow, time between two pulses grow. The maximal to which it can to grow is to the next when this pulse reach this pulse. Yeah, when they actually match the next this pulse which was fired now will actually coincide with the next pulse on the second channel, and we get the same situation, but the pulses will be shifted, but we couldn't distinguish the pulse with a number, let's say number n, and the number n and number n plus 1. We just couldn't distinguish that. That's why when the phase shift, if the phase shift grow, so the length is growing and the indication of the amp is growing because the average is growing, and it's continuous until the pulse of this shifted pulse will coincide with the next pulse of the first channel. At this moment, we get a situation when we actually get some kind of drop back. So when it reach the previous pulse, it's actually the situation will be when these pulses come simultaneously. They provide this, how to say, this provides this prohibited, there will be the prohibited situation when both S and R is on 1. We may select special design for such kind of trigger when this switching of both to 1 doesn't provide it, doesn't give anything. So trigger just doesn't switch to the other state. But when we continue to increase the period, this pulse which actually reached or actually coincide with the first channel pulse will continue to move on our picture, continue to move left, and finally we get the same situation as the very beginning of this experiment when we have just a small phase shift. So this meter could not distinguish the shifts, couldn't distinguish shifts which are more than 2 pi or more than 1 period. So it could measure shifts only up to 1 period, because when the shift increased or overgrow 1 period, we couldn't distinguish it. We still consider that it's just smaller shift, but with a higher, but just a smaller shift. But indeed, in fact, we may get a shift which is higher than 1 period, yeah, but we couldn't distinguish it from the small shift. Well, so actually the problem for the all phase meters, the same is for this. So actually phase meters that very often could not distinguish, especially analog phase meters, they just could not distinguish the phase shift that is higher than 2 pi, higher than 1 period. Okay, so this is shortly about how we measure the, the phase shift. And now let's discuss how do we measure frequency. But still we still have to, yeah, we have time, yeah. So one of the methods very well known is so-called Lissajous method, which uses scope. I actually have not added here the absolutely straightforward method to measure frequency using the scope. Just use this illustration. So to measure the frequency, so what should we do? We just take this distance, and using the scope, we just measure what is this time between this point and this point, or between maxima, and then divide 1 by this time, we will calculate the frequency. So actually we measure the period with the scope, and then we get a frequency. This method is not so very accurate, because it's not so, we couldn't very accurately define these points, the crossing points or maximum points. So it's just because of the limited limited resolution of the of this picture on the screen, because we always have some width of the line on the screen, and it's we couldn't measure this distance more accurately than the width of the line. Well, so that's why this is very simple method, but quite inaccurate. If we're going to measure very accurately, so we may use this frequency measurement with the Lissajous method. Now, this method is quite complicated from the, let's say, from the setup point of view, because what we need to measure frequency of the unknown source with the Lissajous method, we have to have a scope, and we have to have a reference generator with a which frequency we know well and may change. So we need additional source of the harmonic signal. Another limitation of Lissajous method, we may measure this frequency of the harmonic signal only. Generally, we may use it with some signals which are close to harmonic, but then the shape of the figures will be very unclear. It absolutely doesn't work with a rectangular signal, because the Lissajous figure for the rectangular signals will be absolutely, let's say, imperceptible. We couldn't even understand what we are what we are seeing on the screen. So generally, Lissajous method is used for the harmonic signals, and it's used very often when we need a very accurate frequency measurement, because the accuracy of the Lissajous method is defined by this reference generator accuracy. So what's the idea of the method? So the idea of the method is to take unknown frequency and put it on the scope, on the one of the channel of the scope, and take the known frequency from the generator and put it on the second channel of the scope. As a result, we see some line on the screen. The line depends on what is the ratio between the generator frequency and measured frequency. When this ratio is equal to 1, what do we see? When the generator frequency and the measured signal frequency will coincide, what will we see on the screen when the frequency are equal? No, generally it's maybe line 2, but in most, let's say, in the most common case, we see an ellipse. And moreover, usually it's very difficult in real measurement to get this ellipse still. It's usually a little bit rotate. Why it is rotating? Because we never have a same phase, yeah? Because we never have an ideal generators and ideal signal sources. And the smallest teeny differences in the frequencies actually cause the constant phase shift between one signal and another, because frequencies are the difference is very small, and we actually could write that the frequency of the measured signal is omega, but the generator shows that omega plus some small delta omega, which is very small, which actually as a result the picture behaves as a picture of two similar signals with the same frequency, but with a changing phase. A little bit change of this small change in the phase causes the ellipse to rotate. It rotates around this diagonal. So it becomes line, then grows back into ellipse 2, then become line 1 more, and so on. And if really we have a very stable source signal and very stable reference signal, this ellipse nearly still we may got it still. And when we see this still ellipse, it means that the frequency of the measured signal and frequency of the reference signal are equals. Sometimes the similar, quite not similar, but yes, to some extent similar situation when we see some particular shape on a screen will appear every time when the ratio between measured frequency and the reference frequency is a ratio of the whole numbers. For instance, if the ratio between one frequency and the first frequency and the second frequency exactly 2 on 1 second, not important, yeah, we see such kind of figure. No, it's quite clearly what does it mean. It means that while in x direction our signal change from 0 to maximum, back to 0 and back to minimum and equal to 0. For this time, the y signal have time to change to maximum, then to 0, then to minimum, one more to 0, one more to maximum, one more to 0, to minimum, and to 0. So while an x signal has a 1 oscillation, for the same time, y have 1, 2 oscillation. 1, 2. And as a result, we see such a nice figure. Well, this figure is such kind of figures. They all are named as Lissajous figure, because Lissajous was the first physicist who described such a figures. And we may use these figures to measure the, to compare, or to actually to compare the unknown frequency with the reference frequency. And it's make our measurement a little bit more convenient, so it's not necessary to have accurately the same frequency. We may take a generator, reference generator, that may provide only half of our frequency or double frequency. Usually for the practical measurements, we very seldom use very, let's say, very different, very big these ratio numbers. So actually, the convenient numbers is when one frequency is a 2 times higher or smaller than another, or 2 times higher or smaller, or the ratio between frequencies is equal to 2 to 3 or 3 to 2. It's very seldom that someone takes some other ratio, some kind 3 to 4 or 7 to 8. It's the figure, the resulting figure, it's very difficult to count, to understand to which ratio this figure corresponds. Actually, the general rule, when we look at this figure, we actually try to adjust the reference frequency to make this figure as still as possible, and then we actually count how many times the corresponding figure cross horizontal line and a vertical line. So for this example, the horizontal line, the arbitrary horizontal line, is crossed on maximum 4 times. So we need to find the maximal number of this crossing. Of course, we may get such a strange situation, when this, could you imagine this figure that it's rotating? So it may, at a certain phase shift between y and x, we get not such a 8, but we get some kind of parabolic shape. But in this parabolic shape, we still have only 2 cross with x-axis and only 1 cross with the vertical axis. So we look at the maximal generally we look at the figure, we look at the maximal possible crossings. So here we have 4 crossing in x direction and only 2 crossing in y direction. So why I say maximal? Because we may find 2 lines. For instance, this line where we have only 3 horizontal crossing, and this line have only 1 horizontal crossing. But we have to find the lines where the maximal is a maximal crossing. Well, and then the ratio between the frequencies is actually the reciprocal ratio of this crossing number. So if I know, for instance, the frequency what is attached, what is given to the x input, and want to calculate frequency to the y input, so I just have to know that the ratio between y frequency and x frequency is equal to the ratio of the x crossing number to y crossing number. So just take this formula and use it, and we will get actually how we actually may get the unknown frequency via knowing frequency. So I said the figure what is used may use a different ratios, but generally the measurement actually happens when we attach our reference generator and our source signal to the scope. We usually see just a colored rectangle because there is no special relationship between frequencies, and we don't see any figures. We see actually just movement of, and we have this beam actually moves in vertical direction and in horizontal direction. This movement is not synchronized, and that's why we see just a rectangle. So all these movements, they actually, they paint over all the rectangle. Then we try to start to adjust the frequency of the reference generator, and finally, from time to time, we will see a more structured figures, and this will be those Lissajous figures. One of the comments with this method doesn't work well with a digital generator. Yeah, so it works better with the analog generator than with the digital generators, because of the digital generator always change the frequency in steps. Analog generator changes more or less continuously, so that it's easily to tune to some particular frequency when we already see this figure. But nevertheless, when this method is used, generally for the regular measurement, we very seldom use this method because it's quite big a headache. So you have to find a scope, you have to find a generator, you have to be sure that your measured signal is an accurate sinusoid and stable sinusoid. But for the etalon measurement, when we try to calibrate one generator using another generator, this method is very well, because the accuracy of this method, as I said, it's really huge. It's just is defined by the accuracy of the reference generator. Some field instruments for the frequency measurement. I mean, the instrument which just show us a frequency. Some very old approach. I actually have seen somewhere such a meters, but they used very rare now. Yeah? So it's a called vibration frequency meter. How it works? It uses the resonant vibration of the separate bars. As we know, if you have some knowledge about how the harmonicas are built, or how the harps are built, so we know that in harp on harmonica, the sound is made by metallic bars which are vibrating under the floor under the airflow. Here we force, this is the same idea. Here we have the same bars, similar bars, metallic bars, which they are named, yeah, actually they are bars indeed, yeah. Versus actually they are named not a bar but reeds, because they are flat and thin. Yeah, so these reeds, we force these reeds to vibrate using a coil which actually have a current passed through it. So we pass the measured current with which frequency we are going to measure, through the coil. The coil forces the reeds to vibrate. As the coil magnetic field switched from one direction to another, following the frequency of our current, so the reeds are vibrating with the same current, and the coil actually the effect all the reeds in the same way. So the force the coil apply to the particular reeds are similar. But if the reeds have the same resonant frequency as a switching of the coil, of the field direction, it means the same frequency as the measured current, so then the force from the coil will be applied in the resonant, yeah, and we have the effect of the of amplification of the oscillation of the reed because of the resonance. So if the force applied match with the resonant frequency, so then the reed, which internal frequency or its own frequency, oscillation frequency or resonant frequency, correspond with the frequency of the current, will oscillate with the highest amplitude. So here we see, so if we look at this reed from the top, yeah, so when they all are vibrating, so we see that they vibrate in with a different amplitude. We don't see the position of the particular reed because the vibration is very fast. But we see that some of the reeds are vibrating more than others, and the highest amplitude of vibration will be at that reed, which has a frequency equal to the frequency of the current we measure. Such type of vibration meter doesn't have a very high range usually, and one of the examples when they was used, it's in electrotechnic, and particularly for the measurement of the frequency of the AC current on power stations. Because the power stations have to be regulated in such a way that they have always to produce the current of the same frequency. Otherwise, they will have a conflict with another power station, and all the power system actually drops. Yeah? To prevent it, the power stations control the rotation of their generator and the frequency of the current very carefully. And this was one of the first devices which was actually used to control the frequency of the current that power station is producing. From the illustration, you may easily understand for which country was designed, the frequency meter was designed. Yeah? It's certainly designed for the United States, because the United States have a 60 hertz standard. So this meter is actually designed to show frequency from 55 to 65 hertz. So these meters was not very wide ranged, because the most main application of such a meters was a control of the frequency on the power station. So for the Europe, it should be tuned to have a middle in 60 hertz. For the United States, it has to be tuned to have a middle in the 60 hertz. So that's why the range is from 55 to 65. For the European one, it will be from 45 to 55. Yeah? So this is one quite interesting method to measure. Of course, I demonstrated just for like for the curiosity, because to my mind the solution is quite an elegant, some kind of mechanical vibration frequency meter. Well, now we have to have a big break, and we continue after the break, 15:20. Yep.